organizers for inviting me here to this great workshop. So I'm going to be talking about some of my work with Kanan and Donna. I'm not very good with these clickers. Good, okay. Good. So just 15 seconds to let you get used to the sound of my voice. I'm going to be explaining about a new model we have for interacting with probability distributions. It lets you have some fun with algorithms. And we'll be looking specifically at property testing algorithms in this new model. So I'll tell you about the model. I'll tell you about some of the property testing results that we have in this model and explain some kind of more generic tools, things we can do in this model. And if I have a little bit of time at the end, I'll say just a word or two about some of the applications of the tools I'll mention. Okay, so we've heard, I think, a lot about this general framework already in this workshop, so I'll keep the basic setup for property testing of distributions brief, but just to remind you of sort of the framework of what I'm talking about. Everything I'll say in this talk is about very simple distributions over a finite set, the set of integers 1 through n. And think of n as big N, it's a colossal number. So we have some unknown probability distribution over this domain, and it's a framework where you have some kind of oracle access to the distribution. The usual model, peeking ahead a little bit, is that the kind of oracle you can access is a sampling oracle, what we call just you press a button and you get an IID draw from the distribution. Okay, so that's the standard oracle, that's the standard model, but the talk will actually be about a different model. But just to have, so the basic framework, you have a distribution, you don't know what it is, you can access it somehow through an oracle, the standard model we just explained. There's a property of interest, so some distributions have this property that you care about, some distributions don't have the property. And what do we want to do? We want to make a small number of calls to the oracle, as small as possible. Certainly we want it to be sublinear in n, the size of the support size of the distribution, and we'd like to be able to distinguish between two cases. The first case is that the unknown distribution has the property, and the second case is that the distribution not only doesn't have the property, but it's far from having the property. It's far in some distance measure from all distributions with the property. So in sort of computer science speak, we would think of this as like a promise problem, right? You're sort of promised that the distribution either has the property or is far from having the property. Okay? So in the standard setup, like I said, we would think of the type of oracle you have access to as just independent draws from the distribution. We want to solve our problem with as few draws as possible. And the standard setup, and the setup I'll be talking about throughout this talk, is that the distance measure, how far is this distribution from that one, is just L1 distance, total variation distance. Okay? So you really don't need to read this sort of lengthy definition of the testing algorithm. Maybe just look at the first line of the definition. I want to emphasize the fact that a testing algorithm within a particular sort of oracle framework, right? If you have some type of oracle access to the distribution, then you want to make as few calls as possible to the oracle. You want to, with high probability, say 2/3, say yes if the distribution has the property, and say no if the distribution is epsilon far from having the property. Okay? So a familiar setup from previous talks. Just a couple of standard remarks about this kind of framework. Again, it's a promise problem, so we don't care what happens if your distribution is close to having the property, but it doesn't quite have the property. Think of it as if you never have to deal with such a distribution. The sort of confidence of, you want to be right with probability 2/3 in each case is arbitrary. You can always boost that in standard ways. You can think about frameworks where you have several oracles. So maybe you have two distributions, and you want to know, are these two distributions the same, or are they far from each other? So you have one oracle for accessing each distribution. And again, the kind of thing we're going to be obsessively concerned with is the sort of query complexity. How many calls do we have to make to the oracle? We won't worry about the running time of algorithms. Okay? Okay, so it's a pretty simple framework. Let me instantiate it in a concrete way. We'll return to this example later. Think of maybe the simplest property in the world, just the property of uniformity, being the uniform distribution. So we can always think of a property as just a set of objects that have the property. Excuse me, in this case, the set of objects is extremely simple. It's just the set with one element, the uniform distribution. The distance to the property is just the variation distance between your distribution D and the uniform distribution. It's the only guy in the set. And how does distribution testing work in this standard model where you have a sampling oracle? You just get IID draws. Well, kind of all algorithms work the same way. You press the button a bunch of times, get some draws from the distribution, then you do some computation, some analysis of the samples that you got. For instance, if you're testing uniformity, the standard algorithms, Greg referred to them yesterday, work by essentially counting collisions, seeing how many collisions you get, and if it's too many or too few, you say you think it's uniform or far from uniform. So you draw your points, you process them somehow, and you output accept or reject based on the result. And all algorithms in this sort of standard sampling model have to work this way because there's nothing else they can do. They get the data, they process it, and they make a decision. Okay? So that's the standard framework. Just to briefly recap some results again, I think we've heard about already in this workshop. In this kind of standard model, many very simple and very natural properties of probability distributions can be tested in a sublinear number of queries, but not in a really dramatically sublinear number of queries. So most properties you might be interested in still are going to require something like square root of n, square root of the domain size number of queries in order to do this kind of testing too. So some examples here that I know we've seen already in the workshop. Testing uniformity, we have very tight bounds, essentially square root of n over epsilon squared. Many samples are required, necessary and sufficient. Testing equivalence to a known distribution. Greg gave us tight bounds on that yesterday, so I should get rid of this tilde. Testing equivalence of two unknown distributions. We know what the sort of lay of the land is for these types of problems, and it's always somewhere in the polynomial regime, right? So square root of n is fantastic. It's a lot better than n. But if n is really, really colossal, it still may be too many samples, right? More calls to the oracle than you would like to make. So that sort of motivates this work. We tried to think about other models, other forms of access you might conceivably have to a distribution, and see what can you say about algorithms given these other forms of access. So in this model, the rest of the talk I'll be talking about the new model. Our model is, I guess we call it a conditional sampling oracle. How does it work? So it's not a framework anymore where you just press a button and get a draw from the distribution. Instead, the algorithm that calls the oracle gets to do something, right? It gets to specify a subset of the domain. And what does it get back? It doesn't get a drawback from the whole distribution. It gets a drawback from the distribution conditioned on it landing in that subset. So this is what I mean by sort of a conditional sample, right? You say, please give me an outcome conditioned on this subset of the possible outcomes, okay? And I don't want to get into a long song and dance about trying to justify the model. That may be a hopeless task, but you can think of it as, maybe being a very rough first approximation to a scenario where you're doing some kind of scientific experiment, and you can control, in some sense, some of the parameters of the experiment and restrict the range of outcomes in that way. You introduce a chemical agent into your Petri dish and kill all the bacteria which can't tolerate that agent. So now when you pick a random bacteria, it's drawn from the... This is embarrassing. Okay, let me... keep going. Yeah, so it's a sort of a kind of more precise definition of the model. This condoracle, just to get you used to the notation, you give it a subset S, again, just what I said before, and you get back a draw from the conditional distribution conditioned on the subset S. Okay, so I think it's a very simple kind of framework. Good. So just to say a couple of things, this is a generalization of the usual sampling model. The usual sampling model, of course, corresponds to just you don't do conditioning, you do trivial conditioning and take the whole thing. If you like playing around with algorithms, you might enjoy this model because it lets you do more sorts of interesting things, right? You're not restricted to just hitting the button a bunch of times, doing some analysis of the sample, and then outputting an answer. You can have adaptive algorithms, and indeed you sort of should have adaptive algorithms in this kind of framework, right? You hit the button a couple of times, see where a few of the points live, and now you say, oh, based on this, I want to condition on this piece of the domain, and see what I get if I sort of zero in on this portion of the domain, and so on. So one very natural criticism, which you guys were all too nice to make on the last slide, is that it may be wildly unrealistic to say, hey, what you as the algorithm calling the oracle get to give is an arbitrary subset of this domain, right? I was just blathering on about how huge this domain is, this capital N element set. Can you really specify realistically like an arbitrary subset of this set as a call to the oracle? That might be too much to reasonably expect. So we study a couple of variants of the model in which you can only sort of make these conditional queries on sets with very simple or concise structure. So one of them is this P is for pair cond model. So you can make sort of standard sample calls, give me an arbitrary point, give me a draw from the whole distribution. Or you can say, just here are 2 points, and I just want to draw a condition on it being one of these 2 points. So I don't think this is totally crazy. Maybe you have some kind of expert, and he's not comfortable, sort of having a mental model of the conditional distribution over an arbitrary bizarre subset, but if you present him with 2 possible things which might happen in his domain of expertise, he'll say to you, I think this one is 5 times as likely as the other one, something like that. So some kind of comparison, essentially, type of thing is what you can do in this pair cond model. This other variant of the model, I cond, I is for interval, just you get to query an interval. So you have to think of the points 1 through n as, not being butterflies or fish or something, but actual ordered values 1 through n, right? And then you can say, I want to zero in on this interval of the domain, so on and so forth, okay? And similar models were also studied around the same time that we started thinking about this in work of Chakrabarty et al. They gave some very nice results, which have kind of a disjoint flavor to what I'll tell you about. Okay, so the basic question, we have this model, right? Is it worth studying? Do algorithms in this model can they do more? Can they be more efficient? Can they solve problems with fewer queries than in the standard sampling model? And the answer is yes. In many cases, they can be exponentially more efficient. In fact, for all of the problems that we studied, they're at least exponentially more efficient than the standard model algorithms. So here's a table which may cause your eyes to glaze over a little bit. It's a fraction of the actual table in the paper. If you just want to zoom in and sort of see the qualitative sort of point to take away from this is that in the standard model, for these different types of problems, right? So you've got a known distribution D star, and you have an unknown distribution D, that's the one your oracle is for, and you want to know, is D the same as D star or far from D star? Or maybe you've got two unknown distributions, D1 and D2, and you want to know, are these the same distribution or far from each other? So for these different types of problems, in the standard model, you always need a polynomial dependence on n in order to solve these testing problems. And in the conditional sampling model, sometimes you can solve them with a number of queries completely independent of n. But even in the worst cases, you never need more than a polylogarithmic number of queries as a function of n. Okay. So the model gives you very considerable power, potential efficiency savings.
Can you remind us what's the cond and p-cond?
Yeah, good. So cond is a model where you get to ask you as the guy who's invoking the oracle, get to give it an arbitrary subset. Yes, that's right. P-cond is you just get to give it either a 2-point subset or a draw from the standard sample. And I-cond, which I guess didn't make it onto this table, you get to give it an interval. Okay. Good. Okay, so in the rest of the talk, I'll sketch the ideas behind a couple of these specific algorithms. So testing uniformity, testing identity to a known distribution. After that, I'll tell you about some kind of tools. I used to think of these tools as sort of analogous to like the Koshulevitz-Mansour algorithm in uniform distribution learning, right? It's like a basic thing you want to do in that framework is estimate a Fourier coefficient, right? What are some basic things you might want to be able to do to a distribution or learn about a distribution in our setting? So I'll tell you about some tools, and I think I have one slide at the end on sort of how you can apply the tools. Okay, question, yeah?
The domain chosen adaptively based on the previous thing?
Just think of the sorry, do you mean the set that the tester gives to the?
These, right?
There's like one fixed D that you want to understand something about, and if you're the testing algorithm, maybe the first thing you do is you just draw a random sample. The second thing you do is you draw another random sample, and then you say, oh, based on these samples, I'm going to provide this set S, and I'm going to get a conditional sample.
So it's adaptive.
It's adaptive, yeah. Yeah, in fact, most of the interesting aspects of the algorithms come from adaptivity. Okay. So let's talk about the simplest problem. We touched on this already, testing whether your distribution is uniform or far from uniform. And just to remind you again, in the standard model, if you just get to draw IID points from the distribution, you need square root of n over epsilon squared samples to solve this problem. And just to very briefly sketch the lower bound, really all I should have on this slide is the words birthday paradox, right? I mean, if your distribution is uniform and you make root n over 100 calls, you're just going to see root n over 100 different points. And if your distribution is not uniform, but it's uniform over, say, a random subset of half the domain, then again, right, if I chose the subset randomly, sort of behind the scenes before the process starts, and you make root n over 100 random calls, you're going to see, again, a completely uniform random subset of root n over 100 distinct points. So just a quick sketch that, you really need something like root n many samples if you just have IID draws from the distribution to distinguish between uniform and something far from uniform. Okay? So how do we get more power in the cond model? Well, we get a lot more power even just the pair cond model for a problem like this in a very simple way. So you can solve this problem with 1 over epsilon squared queries. And in fact, this is tight. You can show you need 1 over epsilon squared queries. And how do you do it? You can do it in the simplest possible way, just by a couple of basic observations. So suppose your distribution is far from uniform. Okay, uniform would be like a flat histogram. This guy is like below somewhere and above somewhere and so on. So what does that mean if it's far from uniform? Well, there must be a lot of points which are quite light, which are significantly lighter than like 1 over n mass, right? This is kind of obvious. And there must, again, it's far from uniform. The other side of like, you've got your valleys and you've got your hills. There must be a lot of weight on heavy points, points which weigh a lot more than 1 over n. There may only be 2 heavy points or 1 heavy point, but they have to have a lot of weight for it to be far from uniform. Okay? So this is good because points of the first type, type A, there are a lot of these points that are very light, and I can just pick random elements of the domain on my own without invoking the oracle at all, and I'll find such points. Okay? On the other hand, points which are very heavy under the distribution, I can call the oracle, just the honest-to-goodness like sampling oracle. I can just make IID draws from the distribution, and I'll get some heavy points. So now I have a bag of points over here, and one of these points is light. lighter than 1 over n. I have a bag of points over here. One of these points is heavier than 1 over n. And if I can make conditional samples just on a pair of points, I'll try a point from here and a point from here. I'll query that pair, a bunch of times, and I'll see if I tend to get this point a lot more than I get this point, then it means this point was a lot heavier than this point, and it wasn't uniform. Okay, so if you implement this with a little bit of care, you can get 1 over epsilon squared samples for testing uniformity, and all we're using, again, are these pair cond queries on pairs of points. Yeah?
I'm a little bit confused with the model still.
Sure, yeah.
So, sampling according to D is standard model, right?
Sampling according to D is the standard model. The pair model, you get to make samples according to D, and you get to make a conditional query on a subset of size 2.
Yes. But
Okay.
then you also allow sampling uniformly.
Well, I can just pick a random number 1 through n. You can't stop me from doing that. Toss some coins and
Oh, I see. So that's not really sampling.
That's no. Yeah, there's no. I think. Yeah, there's no oracle involved in this step. I'm just sampling these points. Yeah, I should have said.
Oh, I see. So this is
toss.
not actually using any oracle.
This first line. Yeah, I should have just written tossing log n coins here. Yeah, exactly. Sorry. Question. Yeah.
Isn't there sample complexity 1 over epsilon then? Or do you count the 1 over epsilon?
No. So the expensive step is actually using the pair con to compare these
You have
points.
to call it a few times to get reliable estimates.
You have to call it a few times to get reliable estimates. You actually want to do something a little smarter than checking all 1 over epsilon squared, this point versus this point. That would cost you something like 1 over epsilon to the 4th, I think. So you do it in a smarter way, and you can get 1 over epsilon squared. Yeah. Even though you're checking 1 over epsilon squared pairs, you can sort of amortize the cost. Yeah, sure.
In the previous slide, you mentioned the uniform on a subset of points. So then how do you do conditional pairwise thing for things outside that support?
Sorry, I didn't catch the question.
So here you said that uniform over a random subset of n.
And this is the lower bound sketch for the standard model, yeah.
Yes, but
Yeah.
not for doing the upper bound. I mean, in general, when say this actually realizes that if the true distribution is uniform on the subset,
Yeah, so what would...
how do you do a pairwise comparison of 2 points outside that
Good
support?
question. So what would happen in this setting? Let's think about that setting. Suppose the distribution is uniform on a random unknown subset of the points. What would happen in the first step? I'm going to choose I'm going to choose a bunch of uniform random points, and some of them will not be in the support of my distribution D. In the second step, I make draws from my distribution D. So I've got a point over here which has weight 0 under the distribution D. I have a point over here which has weight 2 over n under the distribution D. When I call my pair cond oracle on that pair of points, I call it 10 times, and every time it gives me this point.
I guess my question
Yeah.
is not even well defined in general.
I'm calling the oracle on a pair of points which has non-zero mass under the distribution because I call it on one point that I picked uniformly, not using the oracle, just tossing my coins. And the other point is a point that I got for making samples according to D. So it is a well-defined oracle call.
It's a well-defined oracle for your algorithm, but not for the problem in general.
Let's talk about this afterward. I think we're going to get into a digression, yeah. Okay. Okay. So just a little bit of how you extend this to solve a somewhat more general, more interesting problem. Suppose you're not trying to test whether your distribution D is equivalent to the uniform distribution. You're trying to test whether it's equivalent to some other known but arbitrary distribution D star. Okay? So you can't do a trivial extension and just say, well, I'm going to kind of do the same sort of thing with these pair cond calls, right? If you think about the uniformity testing case, right, in the uniform case, everything is equal. So with like 1 over epsilon calls, I can tell whether these 2 points are equal, right, to a pair of these points versus that this point is actually 1 plus epsilon times as heavy as this point. Okay? In the general distribution case, maybe I have 2 points that under D star, the distribution I'm trying to test equality to, they have a very skewed ratio of weights. X star is a lot heavier than Y star. And now I want to figure out under my distribution D, is X star, root n times as heavy as I want to figure out whether X is root n times as heavy as Y, or is it 2 root n times as heavy as Y? Well, I'm going to have to call my oracle root n times in order to distinguish these two cases. Right? So you can't do sort of cheap comparisons the way you can do cheap comparisons if you're comparing things that are of equal magnitude. Okay? So you can't extend the algorithm trivially. You have to be a little bit careful. You look at the points in the domain, and through some slightly careful decomposition, it's possible to show that you can break it up into point subset pairs in such a way that points will be comparable to subsets, right? So the ratio of weight on X to the ratio of weight on this subset Y will be in the sort of constant parameter regime, and then you can invoke the same kind of idea, right? That I'll be able to figure out whether they agree under this distribution and this distribution by making essentially a constant number of sample calls. So it seems to be a little bit more expensive, but we can still do this with a query complexity independent of n. And I should mention, it's not a coincidence that we weren't able to show that in the pair-cond setting, we weren't able to come up with a pair-cond algorithm, something as simple as the uniformity algorithm, for this testing D versus D star problem, and that's not a coincidence. There's a not very difficult construction showing that you actually need a dependence on n, something like square root log n, many queries, if you're only allowing yourself these pair-cond queries. So if you can only compare points, you need a dependence on n. If you get to compare sort of a point versus a subset, then you can do it with query complexity independent of n. Okay, so I'll just probably have time to say a couple of words about some of the tools, and then I'll close. So what are some of these tools I want to tell you about? Well, the very first tool, something we've implicitly been discussing already, which is this sort of comparison oracle, right? If you've got two disjoint subsets of the domain, x and y, very natural thing you'd like to know is, what's sort of the ratio of weight on x versus on y. And it's obviously easy to estimate this kind of thing in the regimes where the ratio is not too skewed. If the ratio is extremely skewed, you can either estimate it or you can say, hey, it's way skewed. This guy's a lot lighter, this guy's a lot heavier, that kind of thing. So comparison is very easy. Let me move on and tell you about another tool which is not quite so easy. So you've got your distribution D. This is the guy you have an oracle for. And you've got some point x, okay? X has a certain amount of weight, which I'm denoting D of x. You might be interested in sort of how typical is this point x? What fraction of the weight of the distribution is on points that have about the same amount of weight as x? Okay, so we're going to call this the gamma neighborhood of x, is the set of points who have, up to some multiplicative 1 plus gamma factor, the same amount of probability mass as x does. Okay, so that's this notion of the gamma neighborhood of x. It turns out in some settings you'd like to be able to figure out how much weight does your distribution D put on the gamma neighborhood of x. So I have a theorem here in quotation marks which says that we have an algorithm which can do this for you. You give it a point x and a parameter gamma, and it'll give you a multiplicatively accurate estimation of the weight of gamma under x. This theorem is in quotation marks and highlighted in red because it's a damnable lie. We can't do this. No algorithm can do this. And if you're interested, you can think about it for a minute or two, why it's impossible for at least two different reasons for any algorithm to actually do this. But we can morally do this. Okay, so it turns out that this is another tool which is useful in some contexts. While you ponder this horrible lie that I've told you, let me move on to the very last tool, and I think the minute or two I have left. This last tool is sort of an approximate oracle for evaluation of the distribution. So what would an exact evaluation oracle be? Well, it would be the simplest thing in the world, right? You've got your distribution, you've got a point x, a sort of exact oracle for evaluating the probability mass function of the distribution would be an oracle where you give it the point, call it I star, and it gives you back a number between 0 and 1, the amount of mass the distribution puts on that point. Boy, it would be great if you had this, but that's crazy, right? This is some transcendental number or something. No oracle is going to tell you that. There's no way to get an exact value. So you say, well, maybe there's an approximate eval oracle. The natural definition is that maybe there's some algorithm where, with high probability, it gives me a good approximation, some high accuracy multiplicative approximation to the amount of mass that the distribution puts on some point. You think about this for a minute, and you see this is also ridiculous, right? How could you conceivably do this? Maybe your point I star either has inverse doubly exponential weight or inverse triply exponential weight. And every other point has a lot more weight than that. You're not going to get any useful information about the amount of weight that's on I star, whether it's in this regime or whether it's in this regime, without making a preposterous number of calls. So this definition is hopeless to meet as well, but also it's ridiculous. Why do you care whether it's inverse doubly exponential or inverse triply exponential, right? These are not parts, this is not an amount of mass that you should really be interested in for your distribution. And indeed, that's what one is ultimately able to achieve for these, sort of the real definition of an approximate eval oracle is what? It's that you've got some error set, there's some subset of the domain which has small mass, which has mass less than epsilon, and for all the points which are not in that small mass region of the domain, you can efficiently get a high quality multiplicative estimate of the amount of mass that the distribution puts on the point. Okay, so this is a pretty powerful thing to be able to do. And it turns out you're able to do this. We can simulate such an oracle given just a polylogarithmic number of calls to the conditional oracle. Okay, and I think there's a picture, so I'll just show you the picture and then close. This is not really the picture. This is just, a notion of what does it mean to have this approximate eval simulator. You give it the point, it calls cond a couple of times, and it, if the point is in the bad set, it either gives up or it gives you an estimate. If the point is not in the bad set, it gives you an estimate. The picture of how the algorithm works is something like this kind of, not too surprising, binary flowchart. So you've got the entire domain. You're interested in the amount of mass that this point I has. Well, you can just make some samples from the domain, just call the original oracle. If I is heavy, you'll see it, and you'll be able to estimate how much mass it has, so that's great. if I is not heavy, what should you do? You should put the heavy elements to one side, if there are any. You can partition the domain into two random subsets. I will be in one of those subsets. We're going to have I following the red arrow, so I is in this set S1. And now intuitively, you've halved the amount of weight. You've halved the number of elements in this subset, so you're sort of zooming in with magnification 2, and you repeat the process, right? Make some draws from the distribution conditioned on this sample. Did you get I a bunch of times? If you did, if you got I, then you can estimate the weight of I relative to this. If not, throw away the heavy elements in this set, partition randomly into two subpieces, so on and so forth. So you have a logarithmic number of steps. You get high-quality estimates of the ratio of this set to this set, this set to this set, so on and so forth. It's very much like these approaches in approximate counting. You multiply together the estimates at the end once you've reached I in total, and you have a high-quality estimate overall. Okay, I think I should wrap up. So just to briefly state some of the applications, we have for this problem of telling whether two distributions, where you have conditional sample access to both distributions, you're interested in telling whether they're the same or whether they're far from each other. We have two different algorithms for solving this problem. One of them builds off of the estimate neighborhood procedure, this first tool that I mentioned. The other one builds off of this approximate eval procedure. And both these approaches have polylogarithmic query complexity to the different kinds of oracles. And it turns out in follow-up work, Jayadev, Clement, and G have figured out that, in fact, it may be possible to improve on polylog n, but it's not going to be possible to get constant query complexity for this problem. Okay, you actually need some dependence on n to solve this problem. So I think that's it. It's a new model. It gives you a lot more efficient algorithms if you want to run algorithms in this model, and you can imagine a lot of extensions, which hopefully some of you will think about. Thank you. Question, yeah.
Added the number of samples you need to the number of samples. Say you use the rejection sampling to select the subset. So if you add the total number, would you get back your original number of samples?
Or you're asking, I don't think so. I don't think there's a reason to think that rejection sample, like you're saying if you naively simulate these conj queries via rejection sampling, I don't think in general that'll be as efficient as other approaches. Yeah. I mean,
That's the usual number of samples before you hit the comparison, right?
Yeah, I mean, if I'm comparing pairs of points, so I'm going to need, if it is uniform, in order to actually be in a situation where I've gotten this point and this point, you'll make linearly many samples. Yeah.
You promised in the beginning that you're going to talk about some real applications of these ideas.
Oh no, my God, you're not. Yeah, in CS theory, this passes for an application.
Oh, this is application.
Yeah. This is the application of the tool. Yeah. Yeah.
I thought your problem was motivated from some real applications.
No, so Clement has an interest in. I guess there could be Clement has an interest in talking with database people and trying to convince them that got some big data set. Do you want to build this functionality into a database for accessing this set? I let him have those conversations. Yeah.
No, I'm just curious. I'm not a database person. I'm curious what applications there are. So these are the applications. Got it.
I wonder, would it make sense to have a variant in which you charge more for conditional sampling?
Yeah, we thought about this. We had some harebrained ideas about sort of charging according to the complexity of the query. So we thought about, okay, I can specify a pair conj query, it's 2 points, 2 log n. I can specify an interval with 2 log n, an arbitrary query to an arbitrary subset, maybe should be extremely expensive. So you could try to sort of, devise a reasonable cost measure and try to have algorithms which are efficient with respect to that cost. But maybe it's more of a qualitative thing, like, either you believe in the ability to perform these queries or you don't. And so there might be perspectives from which the cost is either infinite for these, for one of these queries, or it's, But you could think about things like that, yeah.
Thank you.